You know what really gets my gears turning? These real-world puzzles. And we've got a pretty juicy one for you today, popped up on an online forum.
Oh, yeah. What's the story?
Okay, picture this. You've got an integrated circuit, MSOP package, soldered onto a PCB, standard stuff, but then it goes through this like grueling test, 1,000 cycles.
1,000. Wow.
Yeah,
Okay.
extreme temperature swings. We're talking minus 40 degrees C, way up to 85 C.
Bone chilling to scorching, basically.
Exactly. And the temperature ramps up and down pretty quick, 4 degrees a minute, and they let it sit at each extreme for like 15 minutes. Talk about stress.
Yeah, that kind of cycling, that's a serious test. Puts significant strain on all the materials,
Yeah.
with the expansion and contraction.
Totally. And the person who posted, they even shared a cross-section image. You could clearly see it, a crack, right there in the solder joint.
Okay, so failure analysis time.
Right, but here's the kicker, the part that makes you kind of scratch your head. Despite this crack, this visible crack, the product, still working.
Huh. Still functional. That is interesting. Incomplete failure.
Exactly. So the big question we're tackling today is why? Why did the solder crack, but the whole thing didn't just, die?
Good question.
So our mission in this deep dive is to explore the potential reasons behind this MSOP solder joint cracking. And we're going to really focus in on the role that differences in the coefficient of thermal expansion, CTE, between the materials might play.
It's a fascinating case. Really highlights that subtle interplay of material science and electronics.
Yeah.
And like you said, the fact it's an MSOP package,
Mm-hmm.
that's a bit unusual for this kind of severe cracking, isn't it?
Right. That's what I thought, too. Now, the original post, it gave us a good starting point, but, well, it was missing some key details.
Always the way, isn't it?
Yeah. Like, we don't know the exact solder paste used or the specifics of the PCD type, thickness, surface finish. Nada.
And the location on the board? Or if other parts failed.
Nope, none of that. Or even if other components nearby had similar issues. It's like trying to solve a puzzle with, half the pieces missing.
Those missing details are often so critical. Solder alloy, for instance, tells you its specific CTE characteristics right away.
Exactly. And just to make sure everyone's on the same page, MSOP. Mini small outline package. It's basically a smaller SOP, tighter pin pitch, like 0.5, 0.65 millimeters maybe. Usually for lower pin count ICs, less than 16 pins typically.
Compact.
Yeah, and what's interesting, like we said, is MSOPs aren't usually the first thing you suspect for solder joint cracks. They're smaller. Joints tend to be pretty resilient.
Compared to, say, big MLCCs, which hate bending, or connectors that see physical stress.
Precisely. So this report of a cracked MSOP definitely got our attention.
It does suggest we need to look beyond maybe the usual suspects. The small size normally means less leverage for stress.
Okay, so the initial buzz on the forum, the first reaction was, CTE mismatch, gotta be CTE.
The classic answer.
Right. Makes sense on the surface. Different materials, different expansion rates when things heat up or cool down. But as you know, just blaming CTE, well, it might be a bit too simple.
It often is. I mean, CTE differences are pretty much always there in electronics. The industry spent decades optimizing materials to handle it.
Especially since it was still working, right? Suggests maybe something else, like mechanical stress, was a bigger player?
Possibly, or at least a significant contributor. It's rarely just CTE unless the mismatch is huge or other factors line up badly.
Okay, so for anyone listening who's maybe not deep into CTE, let's break it down simply. Imagine two materials stuck together. Temp goes up, they grow. Temp goes down, they shrink. But if they grow and shrink at different rates, different CTEs, that puts stress right where they meet.
Yeah, like two people holding hands, one taking giant steps, the other tiny ones. There's going to be tension.
Perfect analogy. So in our MSOP case, there are three main spots where these CTE mismatches could matter. First, between the solder itself and the IC lead frame, usually copper.
Right, the lead frame. That's the metal pathway from the tiny chip inside out to the PCB. Copper's a standard, good conductivity.
Exactly. Now, the forum user didn't say, but we can probably assume it's SEC305 solder. It's super common, lead-free.
Good assumption, industry standard pretty much.
Okay, so SEC305 has a CTE in the ballpark of, 22 to 25 ppm degree C, parts per million per degree Celsius.
Around there, yeah.
And the lead frame, copper, often tin-plated for solderability, copper's CTE is lower, maybe around 16.5 ppm degrees.
So there's a difference. The solder expands and contracts more than the copper lead.
Right, and that difference creates shear stress at that interface, especially when it gets cold, right? The solder shrinks more.
Exactly. That low temp part of the cycle is often where the strain really racks up. Over many cycles, that repeated stress that leads to fatigue cracks forming.
Makes sense, like bending a paper clip back and forth, eventually snap.
Mm-hmm.
And we should probably remember these solders, like Se305, they aren't just tin, silver, copper. They have tiny amounts of other stuff, too.
Trace elements, yeah. They fine-tune the property.
Yeah, I saw a blog post about it, like a bit of silver for toughness, fatigue resistance, a bit of copper for stiffness, strength. It's a real balancing act.
Absolutely. Those trace additions can really impact long-term reliability under thermal and mechanical loads.
Okay, so that's solder to lead frame, interface number 2. Solder to the IC package body itself, that black plastic mold compound.
Ah, yes, the mold compound.
What's the CTE story there?
Generally, mold compounds are lower, maybe 10 to 20 ppm degrees, so usually lower than the solder.
Okay.
And its main job is protection, right? Protect the chips, support the leads. But its own expansion and contraction, well, it can push sideways on the solder joints, lateral forces.
Ah, so it could concentrate stress maybe at the edges where the solder curves up the fillet.
Potentially, yeah.
Yeah.
Especially at the heel or toe of the fillet.
Yeah.
But, these mold compounds, they've been used forever. Their properties are pretty stable, well known.
Okay.
Often the lowest CTE in the whole stack up, actually.
Okay, good point. That brings us to number 3. And this is often the big one, right? Solder to the PCB itself, assuming standard FR4.
Yeah, this is usually the most critical interface for CTE mismatch. FR4, it's tricky.
Oh, so?
Well, it expands differently depending on the direction.
Yeah.
In the X and Y plane, along the surface of the board, the CTE is maybe 14 to 17 ppm degrees C, not too far off from copper or solder.
Okay.
But in the Z-axis, through the thickness, below its glass transition temp, TG, it's already much higher, like 70 to 120 ppm degrees.
Whoa, okay, that's a jump.
And then when you go above TG, which definitely happens during reflow soldering, that Z-axis CTE, the alpha 2 CTE, it can skyrocket 190, 200, even 300 plus ppm degrees.
Jeez. But the source mentioned cracking is less likely during reflow because the solder's melted, right?
Correct. Solder's liquid, it just flows. The stress builds up later during operation, during those repeated temperature cycles.
So even if the product only operates, say, below T.
Right, even below T-jig, that repeated cycling causes expansion and contraction. And that big Z-axis movement, that up and down stretching and squashing of the board thickness, that pulls and pushes on the solder joints connecting the components.
Tearing forces, basically, leading to fatigue over time.
Exactly. Even if the operating temps aren't super high, the board remembers that high temp reflow state, and cycling stresses it relative to that.
So the XY expansion across the board surface is more uniform, maybe less direct stress on one tiny MSOP joint, unless you have really uneven heating.
Generally, yes. The glass fibers in the FR4 do a decent job controlling XY expansion. It's that Z-axis movement through the layers that's harder to constrain and often causes more trouble for the joints.
Okay, let's sum up the CTE likelihood then. You generally need, what, a difference bigger than 10 or 15 ppm degrees C for really significant stress and cracking from CTE alone?
That's a reasonable rule of thumb, yeah.
So looking at the numbers, solder to copper lead frame, maybe 6 to 9 ppm difference. Solder to mold compound, maybe 2 to 15 ppm difference. Solder to FR4XY, maybe 5 to 11 ppm difference.
They're mostly kind of borderline or within that range. Not screamingly high mismatches, assuming standard materials like Se305. If they used, say, a brittle low-temp solder, that's a different story.
Right. So CTE is definitely a factor, adding stress, but maybe not the sole smoking gun here, especially since it still worked. The community thought CTE first, but maybe the evidence points elsewhere.
It seems plausible. That functional aspect really pushes us to consider other things more strongly, like mechanical stress.
Okay, so if it's not just CTE, how do we figure out what really happened? Time to put on our detective hats, I guess.
Indeed. When you face a failure like this, you need a systematic approach. Experience helps, sure, but structure is key.
Okay, walk us through it. Step 1.
Step 1, information gathering. Always. You can't solve anything without the facts. We use the 5W1H framework, who, what, when, where, why, how.
Right.
We need more on the product's application, the exact test profile, manufacturing details, all of it. More info equals better chance of finding the root cause.
Makes sense. The forum post gave us the what cracked joint and some when we're 1,000 cycles, but the why and how are big question marks. Plus those missing details like solder type, PCB specs.
Exactly. So after gathering what we can, step 2, get the actual failed sample. And ideally related devices too.
Ah, the physical evidence.
Yeah. Photos are okay, descriptions are helpful, but nothing beats having the actual cracked board. Avoids misinterpretation. And grab any bits that fell off.
Got it. Handle with care. Okay, samples in the lab. What's next under the microscope?
Step 3, Check solderability and, crucially, inspect the IMC, the intermetallic compound.
IMC. Okay, remind us what that is again.
It's that thin layer that forms right where the solder meets the metal pad on the PCB and where it meets the component lead. It forms during soldering when heat makes the metals react.
And looking at it tells you.
It tells you about the initial soldering quality. Was the reflow profile right? Any process control issues? Oxidation on the parts? A good IMC is key.
So what does a good IMC look like?
Uniform continuous layer, both at the PCB pad and the component lead. If it's patchy or way too thick or has voids, that suggests problems in the initial soldering. But you usually need to cross-section to see it properly, like the forum user did.
Right. And based on that image they shared, what did the IMC look like in this case?
Well, the description said the IMC down at the PCB pad looked good, uniform. So probably means the reflow process and the board finish were okay.
Okay. What about at the lead itself?
Harder to tell, precisely because of the crack right there.
Yeah.
But apparently there was evidence of IMC at the base of the lead, and the growth on the sides of the lead looked normal. Suggests is likely okay there too initially.
So initial soldering probably wasn't the root cause, but you said IMC, even if formed well, can be a weak point.
Yes, absolutely. It's essential for the bond. It is the bond, metallurgically speaking, like mortar in a brick wall. But it's also typically more brittle than the bulk solder alloy itself. So when the joint is stressed, mechanically or thermally, that brittle IMC layer is often where cracks like to start. It's the weakest link in the chain, mechanically speaking.
Gotcha. Okay, so even with good IMC, stress finds the weak spot. What's step 4 in our investigation?
Step 4, examine the crack morphology, the shape, the path it took.
What did the photo suggest?
It looked like the crack probably started right at that IMC interface at the bottom of the MSOP lead. And interestingly, the complete break, the full fracture, seemed to be only at the bottom. The cracks on the sides hadn't gone all the way through, which, as we said, explains why it still worked. Current could still sneak through the partly cracked sides.
Makes perfect sense.
Yeah.
And reinforces the idea that the IMC was the point of failure initiation.
Exactly. And ideally, you'd want to look at other leads on that same MSOP. See if they show similar early signs of cracking. Is it just one pin or systemic?
Right, get the bigger picture. Now, switching gears slightly, that number, the 1,000 cycles, the source material pointed out that's pretty extreme for typical commercial stuff, yeah.
Oh, absolutely. Standard reliability test, maybe simulating shipping. You might do 5, 10 cycles, maybe 100 for some things, 1,000 cycles like that. That's more like component qualification or high-rel stuff, automotive, aerospace, military.
So it makes you wonder about the product's intended use. Why such intense testing?
It does. And it really makes you think maybe something beyond just inherent material properties was at play. Was the board itself flexing a lot under those conditions?
Good question. And the source author also wondered why they did a destructive cross-section after finding it still worked. Maybe just routine inspection found it.
That's plausible.
Yeah.
Sometimes non-destructive tests, like X-ray, might miss fine cracks like that. Cross-sectioning gives you the definitive answer.
Okay, so let's recap. CTE mismatch. Probably a factor, but maybe not the main driver alone. Initial solder quality IMC looked okay based on the limited info. So where does that leave us? The source material strongly suggests mechanical or bending stress as the most likely culprit. Why that?
Well, if the usual suspects aren't clearly guilty, you look for other forces. And PCB warpage during temp cycling is a huge one.
Warpage? How does that happen?
Multi-layer boards. They're complex structures. Copper layers, insulation, vias maze. They don't all expand and contract perfectly evenly, especially with big temperature swings. This unevenness causes the board to, well, warp, bend, flex, twist slightly.
And that slight bending stresses the components sitting on top.
Exactly. The components are rigid. The board beneath them is flexing. That force gets transmitted straight into the solder joints, holding them down. And over 1,000 cycles of that bending back and forth, that's classic fatigue. Causes cracks, often with those telltale branch patterns as the crack finds the easiest path.
And thinner boards would warp more, right? Less rigid.
Generally, yes. And location matters too. Components far from mounting points, far from where the PCB is screwed down to the chassis. They often see more stress.
Because the board flexes more out in the middle.
Right. Or if the chassis itself deforms with temperature, it can pull or push on the PCB, and those components out on their own become the stress relief points. Their solder joints take the hit.
Okay, that sounds like a very plausible explanation for this case. So if PCB bending mechanical stress is the likely villain, what can engineers do to stop it?
Countermeasures.
Several options. First, Design phase. You can use CAD simulation, finite element analysis, FEA.
To predict the stress.
Exactly. Simulate the temperature cycles on the whole assembly, PCB and chassis, see where it deforms most. Then you can modify the design.
Oh.
Maybe change screw locations, add more mounting points, maybe move sensitive components like this MSOP to a less flexy part of the board, or add stiffeners to the chassis, or even choose a more rigid PCB material, though that costs more.
Makes sense. Address the root cause in the design. What about manufacturing process fixes? The source mentioned underfill.
Yes, underfill. Basically squirting epoxy under the component, between it and the PCB.
To reinforce the joints. Right. It adds mechanical support, helps distribute the stress away from just the solder. It can definitely help.
Yes.
But, as the source wisely pointed out, it often just delays the inevitable if the underlying warpage is still happening. It treats the symptom, not the disease. Eventually, the underfill itself might crack under enough stress.
So it might get you through warranty, but maybe not solve the fundamental problem.
It can be like that sometimes. It's a valid technique, often used, but it's best when combined with addressing the root cause of the stress.
So the best approach is always figure out why it's cracking the root cause, verify it, and then fix that fundamental issue.
Absolutely. That's the path to a truly robust and reliable solution.
Well, this has been a really fascinating deep dive. It's amazing how complex even a simple solder joint failure can be. So many interacting factors.
It really is. And, we have to remember, our whole discussion here is based on assumptions. Given the limited info from that forum post, there could easily be other factors we haven't even touched on.
Absolutely true. And to you, listening, if you have other ideas, alternative takes on this cracked MSOP, we genuinely love to hear them. Solving these engineering puzzles really benefits from different perspectives.
Definitely.
And hey, if you enjoyed digging into electronics manufacturing reliability, stuff like this, make sure you subscribe to our channel.
Please do.
And if you found this chat valuable, maybe give us a like, subscribe, share it around, a 5-star review on your podcast platform. That always helps too.
Helps others find us?
Yep. You can find links to anything related we mentioned down in the show notes or episode info. Thanks so much for tuning in for this deep dive.
Yeah, thanks everyone. Until next time, keep asking questions, keep learning.